Okay, the warm-up says if you were buying hamburgers X and hot dogs Y for a party and need to have at least 6 packs of hot dogs. So that's important. At least 6 packs of hot dogs and at least 10 hamburgers. Which graph could represent this information? So what we're going to do is we know that hamburgers are X. So hamburgers here would be X. And then hot dogs are Y. So at least means that's the smallest amount that you can have. So it's got to be greater than or equal to. Same thing with your X. It has to be greater than or equal to. Well, we know that greater than is shaded above. So we want to shade above both of our lines. Well, so that one doesn't work. This one works because this is the area that's shaded. So your answer is probably B, but it wouldn't hurt to go ahead and check and see if any of the other ones do, and they don't. Okay, so your answer is B because both of those lines are shaded above. Okay, scatter plots can follow many different shapes or patterns such as linear, quadratic, exponential. We're going to try to focus on identifying linear and exponential models. We're not really going to look at quadratic. So if we're looking at graph A and graph B, we're going to identify which model has the best fit for the data. So it's basically saying, is it linear or is it exponential? That's what it's asking you. Is it going to be a linear model or is it an exponential model? Well, this looks like I can probably just draw a straight line through it. So that's linear. And then we go over to graph B and you can see that it definitely has that curve in there that exponential models have. So exponential. Exponential model would be better for that one. So that's basically all you're going to be looking at today. All right, so this one it says look at the data in the graph provided, then find a linear best fit using the calculator. So it asked me to do a linear best fit. Even though this graph kind of looks like it's exponential, it told me to do a linear best fit. So this is where you're going to do like we did yesterday. We're going to go to our second data, start entering your data as your X's and your Y's, and then you're going to go ahead and look for your A and your B value and your R value so that you can write your equation. So go ahead and pause the video and put those into your calculator. Okay, the A and B value that you should have got, your A would have been 7.57, and then you've got that X there because we're writing an equation. And then your B value is negative 18.01. You can just round to 2 decimal places on these. And your R value is 0.87. Okay, so see that it's not necessarily a strong, like a really strong fit because it's 0.87. Usually we see 0.9s in there. So that tells me that this might not be a good model. A linear model doesn't fit it as well. So then it says, what shape do you notice the data made? Well, it's exponential. Because there again, it's got this nice curve in it that tells me that it's probably exponential. Do you think that a linear equation is the best fit for this data? No, definitely not. I think that an exponential would. So it says what equation would work better? Definitely exponential. So it's pretty simple. All right, let's look at example 2. On this one, you actually have to plot the data. So go ahead and take a second and do that, and I will as well. So 4 is 24. 8 is 28. Hopefully this is pretty easy to graph for you. 12 is 30. 16 is 32. 20 is 36. 24 is 39, which is almost 40. And then 28 is 43, which is almost all the way to the top. Okay, so you can see your data there. And then it says use the given set of data, plot the data. and determine if this should be an exponential or linear model. Well, based on what I graphed, it looks like I could probably draw a pretty straight line through them, so I would say linear. So a linear model would best fit that data. Okay, example 3. These should go pretty quick just because all you're doing is looking at the shape. So on this one, go ahead and start graphing. And if you notice that it is actually counting by 100s, because this one right here would be 700, and then 800, and then that one's 900. It's just not labeled every 100. So when you see 6.33 and that's at 0, I mean, you can just get as close as you can. It doesn't have to be exact on these. So then 1 is even a little bit higher. 2 is 793, so that's almost 800. 3 is 794, a little bit taller than the one before it. If they look like they're right next to each other, it's okay. These are really hard to graph on this one. So 4 is right on the dot there for 1,100. And then you've got 1309, so just barely above 13. And then 6 is 1771, so almost 1,800. And then 2,288, which is almost, oops, that's a little too high. There we go. Okay, so now that we look at our data that's graphed, what shape does it look like it made? It looks like it's got that curve in there still. So I would say that it's exponential. Okay, so now that we're done plotting all of those, we're going to look at these and we're just going to describe which one we think it would be, either linear, exponential, or neither. Now, if there's something that doesn't have a pattern at all, or a pattern that we haven't seen before, then I might say neither. This one's definitely exponential. I'm just going to abbreviate. This one doesn't really look like it has a complete pattern on number 5. So I don't know that I would say exponential or linear for this one, so I would say neither. On number 6, looks like it's got a pretty good straight line going there. It's probably a weak positive correlation, but I would still say it's linear. And then for example 7, this one still, it looks like it kind of curves a little. So even though it's not a very steep curve, I would still say exponential. Okay? All right, correlation versus causation. Now this can be really confusing if you don't really listen and kind of understand what I'm talking about. So make sure that you're listening really good to this. Correlation. A correlation exists between two variables when one of them is related, so it is related to the other in some way, but they do not affect one another. Okay, we're going to go through several examples, so you'll get it in a second. But just remember that correlation, just because something's correlated to each other, doesn't mean that you have a cause and effect. So because something happens, it's not going to cause something else to happen. Okay, causation is when one event causes another event. It definitely causes the other event. Okay, so let's go through some examples and see what we have. So it says, example 8, it says if buying sunglasses is correlated with buying ice cream, does buying sunglasses cause one to buy ice cream? It's asking, does it cause it? Well, why do you think that people might buy sunglasses and buy ice cream at the same time? They might be both during the summer. Maybe some people buy ice cream in the summer. But just because I buy sunglasses doesn't mean that I have to, 100% have to, buy ice cream. So I would say no, it does not cause it. It's a correlation. Not causation. Okay, so just because I buy sunglasses does not mean that I have to buy ice cream. Now, you might want to buy ice cream because it's hot outside, and you might want to buy sunglasses because it's all sunny, but that doesn't mean that they are actually making one another happen. That's the difference between a causation and a correlation. And with these, there can be a lot of what ifs, but if you say what if, then you're not thinking about it truly. So you need to just completely read what is there and then say, how does this happen? Does it definitely affect the other? Okay, so example 9. According to the Washington Post, an NFL team has successfully predicted the outcome of the presidential election since 1940. A win for the Redskins means that the incumbent party wins the election, and a loss means that a non-incumbent party will win. The only exception to the Redskins rule came in 2004 when the team lost to Green Bay, but George W. Bush still won the election. This question is, do the Redskins cause who will be president? So obviously, no. Of course it doesn't cause it. They just happen to be correlated. So there again, no. It's correlation, not causation. Okay, so that one was kind of an easy one, of course. That would be stupid to think that. So, no, the Redskins do not do not cause someone to win it. Okay, so example 10, an ice cream sales may increase as soup sales decrease because ice cream sales typically increase in warmer weather and soup sales typically decrease in warmer weather. Nobody wants soup in the summer. So does this mean that the amount of ice cream at a grocery store when it sells, it affects the amount of soup? It affects the amount of soup that's going to be sold. Well, just because people are not buying ice cream doesn't necessarily cause the amount of soup to go down. Some people might like soup in the summer. Okay? So this one again is no. It's correlation, not causation. Okay? All right, example 11. Which of the following statements shows a relationship that is correlated but does not cause the other? So now we're looking for something that is correlated but doesn't actually cause the other thing to happen. Okay, so it says the amount of rainfall received and the level of water in the lake. So if you receive more rainfall, is the water level in the lake going to go up? Yes, that is definitely a cause. And we want something that does not cause it. So that one's not our answer. So B, the number of lights left on each day and the amount, the electric bill. So if I leave the lights on, am I going to be charged for more electricity? Yes, that's definitely a cause. So that's not our answer. The increase of warm, sunny days and the number of ice cream vendors visible. Because it's a warm, sunny day, does it force those ice cream vendors to come outside and actually sell ice cream? No. I mean, they probably do because they know that they'll sell more, but that doesn't mean that they cause it. So this is the correlation. I'm going to abbreviate there. So C would be your answer. I would go ahead and read D just to make sure that you're not misinterpreting one of them. So the number of hours worked and how much money is made. Yes, definitely that's a cause. If you work more hours, the more you get paid. All right, so example 12. Which of the following statements shows a causation relationship and not just a correlated one? So we want a causation this time. So an individual's decision to work on construction and his diagnosis of skin cancer. So if an individual works in construction and he has skin cancer, did his construction working cause him to get skin cancer? It doesn't necessarily cause him. He is more likely to get it, but it doesn't cause him. So this is correlated. Okay, so remember we're looking for a causation, so that's not an answer. Okay, so again it says the decrease in temperature and the increase in attendance at the ice skating rink. So it might necessarily make people want to go ice skating more because it's getting colder outside, but does it force people to go ice skating? And the answer would be no, this is a correlation. Okay, so that's not our answer. As a child's weight increases, so does her vocabulary. So as the child eats more and gains more weight, does she start to talk more? Definitely not. This is correlated. And then the last one says the number of minutes spent exercising and the amount of calories burned. Yes, this definitely. So the number of minutes spent exercising. Since it's telling me that I'm exercising and the amount of calories burned, doesn't matter what kind of exercise you're doing, the more you're doing it, even if it's just walking around the room, you're definitely going to burn more calories. It doesn't say that you're going to lose weight. It just says that you are burning more calories. So yes, this is a causation. So that's definitely our answer on that one because we were looking for a causation. All right, next one says which of the following statements shows a relationship that's correlated but does not cause. So does not cause the other. The number of tardies in the class and the number of detentions received. Well, if you are tardy more times and you get more detentions, does that have a causation effect? And yes, it does. Okay. And if you say, well, what if they don't write you tardies? Well, you're saying what if, so you can't say that. All right, so the season of the year and the number of water-related injuries and deaths. Because it is maybe warmer outside, more people might be on the lakes, so they might have more water-related injuries or deaths. But because it is warmer, does it cause people to die? No. So this is a correlation. So I think that that might be our answer. But we need to go ahead and keep reading just to make sure. So as the temperature rises, the mercury in the thermometer will expand and rise. Yes, that's definitely a cause. And then the longer the dimensions of a rectangular patio, the more square footage there will be, definitely a cause. Okay, so I want you to take just a minute and pause the video and do this whole entire page on your own. And then when you come back, we'll go over it. Okay, so number 14 says, which statement below might cause by the statement, the more the furnace runs. So it's asking, it's going to be caused by this statement. So the more the furnace runs, the less time individuals will spend outside. Well, does that cause someone to stay inside the more the furnace runs? No, definitely not. So that's not an answer. So the more the furnace runs, the longer you will have to let your car warm up. Well, we're looking for something that is causing it. So the more the furnace runs, the furnace is your heater. So the more the heater runs, then it's definitely probably colder outside. So you might want to let your car warm up longer, but it definitely doesn't cause it. So the more the furnace runs, the colder it is outside. So does the furnace running make it cold outside? Definitely not. So then the more the furnace runs, the warmer the house becomes. That's definitely something that's going to cause it. Because if you leave your heat on, then it's going to get hotter. Okay, so it's 15. Consider the large number of countries around the world. There's a positive correlation between the number of Xbox 360 games per person, which is X, and the average life expectancy, which is Y. So positive correlation means that it's going up. So does this mean that we could increase a life expectancy in Rwanda by shipping Xbox 360 games to that country? It's a good question. So if we think that this is definitely going to cause this, then we might want to start shipping those Xbox 360 games. But if it's just something that might be correlated, then definitely not, because it's not going to actually make someone live longer. Okay, so do you think that Xbox 360 games makes people live longer, basically? So I would say no, definitely not. That is correlated. It is not a causation. 16, the sales of television sets have increased, so is the number of overweight adults. Does television cause weight gain? This is something that can probably be argued one way or the other, and if you have a great argument for it, then you can definitely let me know. But because I have a TV, because it says sales of television sets, not because I have watched it for a long time. I could just have like 12 TVs in my house. Does that mean that I'm going to be an overweight adult? No, it does not. So when it says does television, we're talking about the sales of television sets have increased. So has the number of overweight adults. Does owning a TV make you be overweight? And I would say no. Depends on how much you want to watch. So if you just sit there and do nothing, then yes. But notice I said if. So that's correlation, not causation. 17. A study in an elementary school found that children with larger shoe size were better readers than those with smaller shoe sizes. So do big feet make children read better? Well, they might have a larger shoe size because they're older, and they might have a more vocabulary because they're older. But because they have larger feet, is that going to make them read? Will somebody that has the size 9 have the same reading ability as someone else who has the size 9? No. So this is, again, correlation, not causation. Okay, so is there a correlation between eating too much fast foods and gaining weight? So yes, is there a correlation? Yes, probably. Does eating fast food make you gain weight? Well, no. Some people have more metabolism than others, so they could eat whatever they want and never gain a pound. But is there a correlation to it? I would say yes, there definitely is. There's been studies shown that yes, there is a correlation between eating too much fast food. Notice it says too much, and gaining weight. Basically, what you want to make sure that you think about on all these is it 100% all the time going to happen? Okay, so if you can say yes to that, then that's definitely going to be a causation. If it's something that might happen by another outside element, then that's a correlation.